All right. So that's kind of an introduction for tomorrow. We're going to visit quantum source, which is photons and atoms, by the way, and also the Weizmann Institute. And you see there superconductor, which we'll not talk about, but also atoms and photons. I actually saw something nice, also the same, talking about that.
Really?
So this guy, well, did not win any of these. There's no Nobel, and actually he does not have a Pulitzer. He died in 1950, just a year after he had 1994 out, and 5 years after Animal Farm. But there is still a prize you could win. Well, that's a prize, by the way, for political life. Which is interesting. All right, that was the important. Okay, back to computers. So, okay, you saw that. We have qubits, and we need them to fulfill all sorts of tasks. We need to somehow have all the qubits together in a register, and we need to initialize them very, very well. Then we need to be able to control them with high fidelity. We need the ability to split. We need the ability to flip. And then we need to let them interfere. This is where the magic comes in. And then we need to measure very well. So these are kind of all requirements from the modality that will realize this. And I remind you that the magic will only happen if no one, there is no environment or us that look into the computer except if we have a raw correction. So there is a challenge, like as a technical person, if you come to realize this, the challenge is like, how do you tame them? How do you do this puppeteering? How do you both control with very, very high fidelity, very pristine, initialize, hold? Holding means that there is something physical that holds your qubit. Maybe an optical trap that holds the atom. It could be the substrate that holds your superconductor, but something needs to hold it in place. There is a electric trap that holds your ions, but something holds it in place. You need to couple to tell them to interact. Different qubits need to interact. You need to tell them interact now, stop now, and then you need to measure. So this this from one hand. On the other hand, they need to be completely isolated from anything. Okay, nothing should measure them even in principle, which is the switch part information. So that's the biggest challenge. And when people face this in, let's say, 25, 30 years ago, that's how they kind of went to attack this problem. And I wrote other challenges like error correction codes and how you scale up and how it can, okay, this is like a task for people that develop algorithms. But for us physicists that don't do computer science, this is what we are facing with. How you fully isolate, but it's fully controlled. And there is, as you know, these are not the only four, but there is a competition between several modalities. And kind of as a beginning, just let's browse all of them quickly. So you can make qubits out of neutral atoms. These are usually cold atoms, although not necessarily. When we say cold, we mean close to the absolute zero. This is minus 173 degrees Celsius, which is 0 degrees Kelvin. Usually it's in a box in a vacuum chamber. And this represents here the atom with its orbit. And we usually hold them with laser fields. We use laser fields to hold them, initialize, control, and measure. Everything is done with optics. You'll visit Weizmann tomorrow, so you'll see them physically, but this is like pictures from my lab. You see here, for example, a glass vacuum chamber with all the magnets around it, and a lot of lenses. This is where the laser come in from many different angles. And when we turn off the light, if you have a sensitive enough camera, you could see the atoms. This is this spot in here. This has about 100 million atoms in there. Takes about 1 millimeter cube. And this is, by the way, taken with an iPhone camera, but with an iPhone camera that is default, the 4S. So all iPhones from model 5 and above have this IR filter that does not let you take this picture. And then if you need many atoms, you need many laser beams that will focus down and will collect and trap many atoms. And you need, this actually is kind of nice because you can like really imagine them as being separated qubits, and you can address those qubits with light. So these are atoms, and you can ask them, two of them to interact, stop everything you do with lasers. We'll go over that. Okay? If the atoms are not neutral, but rather if they are charged, if they are missing an electron, or like an extra electron, then you can trap them not with light, you can use electric fields to trap them. Usually an electrode. This is a picture from the Weizmann quantum computer based on ions. This is from Boyu Zeri's lab. So actually you see a chip, I don't know if Amit showed you that. And there is an electrode in here, in fact many electrodes, like 100 electrodes. And then you can put ions in there. And the same thing goes, you simply shine light on them and control them. You can also use the trap to control them. Photons, so you should imagine something like that. So photons don't stand still, you don't hold them, they simply fly. So imagine you have like a chip, a photonic chip with channels in it, and things fly from one side to the other, and then you would have these type of beam splitters that could make a photon that come here go into a zero position. This is a Hadamard gate. This would be a phase gate maybe. It would put a phase on this channel but not on that. And then you measure at the end. So we'll try to talk about this as well. And then the fourth is a superconducting circuit. This is also what Google does and IBM does, so I hope you will hear from Google tomorrow, right? If I'm not mistaken. And you will also visit, this is Serge, wasn't Google. Visited quite a lot in this talk. And this is his lab, and you will visit this tomorrow as well. And this is a superconducting circuit in here, inside a cryostat. And the qubits here would be, very heuristically, would be having a current or not having a current in a loop. This is a conductor, and then because it's superconducting, the current can simply flow indefinitely. That would be 1 and 0.
The bigger refrigerator, right?
Yes. Yes. This so the refrigerator is made of like 2 buckets. The bottom bucket is now in here, and so when they want to close it, they will simply lift up the cylinder, and then they will liquid helium will flow in here in order to cool down the circuit.
What is the difference between the dotted circle and the?
Well, that's kind of 0 current and 1 current, 1 quanta of current. More about introduction. This, I'm sure you've heard, not so from me actually at some point, but just for us to have a feeling, we're going to talk now. So we talked up until now maybe about somewhere in here. At some point I said that we're also talking about the borders of this stack. But now we are going to talk about this brown part with a bit of that. And how do we really implement the qubits themselves? Okay. So quantum computing with neutral atoms. And I want actually to start. Did you see that before? The list, the De Vincenzo list? Okay, no, so that's actually good that it's here. This is a list that was compiled by De Vincenzo in 1996. It's only on the archive, so it's not a refereed paper. And it's this guy, David De Vincenzo, listing what he understood as the 5, there are actually 7 if you want to do more, but 5 requirements for a quantum computer. So if he knew about this competition that is going to start, that people will look for viable qubits, and he set the rules for the game, in a sense. And he said, all right, you want a qubit, that's what your qubit should be able, or your system should be able to do. First, there should be something physical in your system that is a qubit and can be like in well-defined 2 states. And this should be a scalable system that you could like, put many of them. For example, first implementations that were done with small molecule NMR machines did not fulfill the Vincenzo criterion number 1, but they were not scalable. You could do, molecules with 6 or 8 atoms, but not much more. Second, you need to be able to initialize which is to put them in a well-defined state, and this should be a, what you call this a fiducial state, like a well-defined state that is unquestionable. Long T1, T2 times, all right, we can argue with the Vincenzo. There should be a way to implement gates, and there is this minimum set of gates, so arbitrary 1 qubit rotation and C naught or something like that. This is of course the most challenging, especially the entangling gates are not trivial. And at the end, you need to be able to measure, and to measure, he called this qubit specific measurement. I will also stress the fact that it should be a state selective measurement. It should be a measurement that tells you what state the qubit is in. And atoms, turn out, they fulfill all of those 5 criteria. I see still people copying on the board. All right, so let's see how they do that. Here is a quantum computer based on arrays of single atoms. This I took from Adam Kaufman and Gila picture. You see here 16 atoms. Each one is held in a focused laser beam. It's in vacuum. We usually use alkali atoms or alkaline earth atoms. Both of these type of atoms, one example is rubidium, the other one is strontium, they have very little number of electrons in the outer shell. The alkalis have only 1, super easy. Okay, put this electron wherever you want, but that's the options that you have. And alkaline earth have 2 electrons in the outer shell. That's the second row in the periodic table. And 2 electrons, it's slightly more complicated, but also give you more capabilities, and this is usually what people use. We don't use, I don't know, gold or something like that. Then, these are put in ordered array, currently only in 2D. You could envision maybe something also in 3D. Each of these dots is an atom, and it is held by taking a laser beam with a very, very good lens and focusing this lens to about a micron, which is almost the wavelength. And then the strong light field at the focus of this laser beam attracts the atom to its center. And as a record, people have done, I think currently the record is 6,000, published like 2 months ago, 6,000 atoms. And people already like 10 years ago demonstrated 3D, like even the Eiffel Tower construction of the atoms. So this is kind of very, very flexible.
It has to be in crystal form, right?
No, it doesn't. No, do whatever you want, because you control the positions of those foci, and you can put them wherever you want. So you can even draw the Mona Lisa.
Is discrete?
It is not discrete. No, this is kind of light field engineering patterns, and you can do whatever you want. It's kind of convenient that they are in square lattice because, for example, you can take 16 of these and you can transfer them, and then they meet other 16. And if you have a gate now, each of the 16 talk to its kind of neighbor and the other one. But other than this convenience, it's not important. All right. Asking question is allowed also in Hebrew. Manipulation and readout is done by more laser fields, others, that are aimed at different atoms. So you can, if you want all of the atoms to undergo a bit flip, you can shine all of them with one big laser beam. But if you want only one of them to say, I don't know, get a bit flip, then you can focus down a bit flip laser on it and perform that. Or you can do that. You can excite 2 atoms to a state. We'll talk about this. That is so strong in terms of its electric dipole that then they start to talk with each other, and this is how you create a gate. And you can do this for particular atoms that you choose. So in principle, and did I skip that? This is a structure. You don't need to understand everything, but it gives you the feeling for how we think about the things. This is strontium, the second in the second row of the periodic table. So it has 2 electrons, and you can see the 2 electrons here are at the ground state. Here the 2 of them are in some other state. Here one is really far, and all of these are states that are like part of this Swiss knife that this atom is, and we can manipulate and go from one to the other using lasers. So all of these are laser transitions. So this was an overview. Now let's even zoom in further. So the way we manipulate states of an atom is by electromagnetic fields, magnetic fields, electric fields, or light, or microwave, or RF, but essentially using light. So here I wrote laser, but you could also imagine other types of electromagnetic fields. And here symbolically what I do, I take an electron from an orbit, and using a laser energy, I put it in a higher orbit. This is called excitation. Here's another option. If I zoom in, this electron has a spin. This spin could be up or down. And these are also two distinguishable states, and I can decide that my qubit is, so if my qubit could be 0 and 1 in two different orbits, it can also be something other, kind of different choice, which is down spin or up spin. Usually, then I would actually use radio frequency or microwave in order to flip them because the energy difference is different. But it's, if you think generally, this is an electromagnetic field, this is an electromagnetic field, and they switch from one state to the other. Okay.
How long it takes to switch?
The shortest would be tens of nanoseconds. That's what people do. Tens of nanoseconds. These will be a bit slower, but not much slower. It still be a microsecond or so.
Actually, the electron changes spin.
Sorry?
Actually, the electron is actually changing spin.
Yeah,
It can go the other way.
Well, spins is
So some kind of.
I mean, imagine a ball that spins, but somehow because it's really round, you don't really see these spins. It's like that's one way to think about it. But there is still a spin there, and then yes, the answer is that it changes. The angular momentum of this electron would change from pointing down to pointing up, and this angular momentum would be given to the atom or taken from the atom using by this field. Another way to depict this is this our favorite level structure. So this is an energy level diagram of the two-level atom. This is the bottom energy, 0, and this is the excited state that requires a particular amount of energy to get to the state 1. Instead of energy, we can think about frequencies, which here I mark as omega A. And if you want, this is the rotation frequency of this atom, of this electron around the atom. Okay? It's not just an illustration. It really is that.
Measure it by time, like this.
Yes, you can think about this as time. Yeah. So this electron, let's look at that. This electron has some oscillation frequency, and this electron has a different oscillation frequency. And the difference between these oscillation frequencies is exactly this. You know how much time it takes? So this is 500 terahertz. 500 terahertz, so this is 10 to the minus 14 seconds. Okay?
To complete one
loop, like 10 femtoseconds. And this would take 1 femtosecond. So the difference would be 1 femtosecond, or hundreds of terahertz, and this would be this frequency. So very, very large, and not really, almost not detected. Okay. You did some Hamiltonian? You did, right? Just a bit, but there wouldn't be a lot. Just to give you a feeling. I'm not going to use it mathematically in any way. The Hamiltonian defines the states of the system, and here I only define one. I only tell it that if the atom is in state 1, then it has this frequency, and if it's not in state 1, it doesn't have this frequency. That's that describes this system. That's the only term you need in order to describe this system. Okay. All right. Now I shine laser on it. The laser is this yellow arrow. The laser can give energy to the atom or take energy from the atom. So it can excite the atom, or it can let it be excited. And in principle, the laser also has a frequency. And I need to match my laser frequency to my atom frequency. We discussed this already. so that the excitation is efficient. Okay? This is a slight mismatch, not good. Okay? And this I describe again in my Hamiltonian with a term that takes 0 and makes it transform it into 1. So it excites the atom. Okay, if I come with a 0, it becomes 1. This represents excitation, and in this term I also put the electric field strength and the frequency of my laser and the phase of my laser. So all of my laser is represented in this term. So I have my atom term and my laser term. All right, I'm missing one more term. Anyone knows what it is? No, that's good, but it's not going to be in a it's going to be separately, but okay. Okay, so I'm missing two terms. I'm missing the environment, but I'm missing one term in the Hamiltonian that is already depicted here.
The focusing globally from up to down.
That's from up to down. This arrow is missing, so let me just edit. This takes us from 1 to 0, and it looks exactly the same with the signs changing, but otherwise it's the same. So the laser can take us from 0 to 1 or from 1 to 0. Hint, the laser will make a NOT gate, an X gate. Right? And that's it. That's everything I need to do in order to describe the system, except for the environment. There is this trick that the physicists use, which is called the go into the interaction picture, which means that I no longer think about this very loud frequency, because it's too loud, I don't care about it. I only think about the difference in the frequency between them. And then you see, I'm left with 3 yellow terms, which are all determined by my laser. I control my laser. I control the frequency of my laser. I can tune it. All right. I control the intensity of my laser, and in fact, I even determine the shape, the duration, and I control the phase of the light in the laser. Changing the phase means, for example, putting a piece of glass in front of it, so to speak, changes the phase. So I control the whole Hamiltonian. I can tell this electron what to do because I control everything from the outside. I can tell it go from 0 to 1, change phase, go from 1 to 0, stay there, wait, go back. Everything I want to do in this qubit, I can do from externally, just playing with my laser. All right? Okay, that's the same thing.
Can you explain again the dotted line? It is explain the phase and the upper dotted line.
The dotted line.
Yeah.
Dotted line is simply to stress that my laser frequency is not exactly my atom frequency, and there is a small difference between them, and so I put a dotted line where my laser comes in so that I can show you the difference. But the dotted line is not a physical state. Ignore it. Yeah. The physical states are these, but I have a mismatch that I put by hand. Okay, deliberately, because I wanted to play with this term. I want to play with 1, 1, 1, 0, and 0, 1 in order to create all sorts of games.
Yeah, but what we learned in the beginning that because it's quanta, you can jump only to certain jumps, right?
No, but
so
I can create superpositions.
residuals.
No, but I can create superpositions. I can, like for example, if there is some mismatch, then I'm not going to get to 1 exactly, but rather the atom will kind of stay in some superposition state, which is maybe good for me because I want superpositions. So often I don't want to use delta equals 0. I don't want to aim exactly. That gives me more control. Show you what kind of control. All right. If delta is 0 and my phase is 0, so suppose that now that's super simple. I think I have a picture. Here is the most simple picture, right? The only thing I have is F, the strength of my laser. By the way, this represents the word field, F. Then 0 will become 1, and 1 will become 0. I'm missing a minus. And if 0 becomes 1 and 1 becomes 0, I get this behavior.
It's field of frequency.
F field, size of the amplitude of the field. I just
frequency.
No, I couldn't find it. So the right letter is omega. Somehow I didn't want to use too many Greek letters. So maybe next time I will. So you see, if I shine my laser exactly on resonance, exactly at the right frequency, And the only thing I do, I turn it on and that's it. Then my atom will go all the way up to 1, and then down to 0, and then again up to 1, and then down to 0, again up to 1. And it will do this indefinitely, and these are called rabbi oscillations. Okay? This is named after Rabbi. And I'll show you Rabbi in a minute. Notice that if I start my laser here and stop exactly here, I know the time, I turn it on and off. By the way, I turn it on and off my laser is simply taking my hand, turn it on, turn it off. The laser could still shine on my hand, but it wouldn't shine the atom. That's important. The laser is still an oscillator, that oscillates is important, but the atom doesn't see it. So I stop exactly here, I transform my atom from 0 to 1. And this is called a pi pulse. Remember, pi pulse takes me all the way 180 degrees from 0 to 1. But I can stop my laser here. And I make a pi half pulse, which makes my atom in a superposition of 0 and 1. So with my laser, I can perform rotations on the Bloch sphere in arbitrary direction. And this is how I make an X gate, and this is how I make an Adamant gate. Just by turning my laser on at the right frequency for the right time. Of course, if I miss it, I introduce some error, which my error correction should then fix.
I don't understand it.
Not yet, but you will.
Already.
You need to think about this expression
What is the
as describing the evolution in time. So I start with the state of the beginning, the initial state of the atom is 0. I start with 0. This doesn't do anything to 0, because this only takes 1 to 0, so this doesn't do anything. So the only thing that starts in the beginning is 0 becoming 1. Okay? So gradually this term does this. When it does this, I enter gradually a superposition of 0 and 1. I still have the part that are remaining in 0 and some parts that are in 1. I start to excite my atom. Somewhere here in the center, there is so much 1 that this term becomes strong, and this term becomes weak. And the excitation slows down until at some point, my atom is fully excited, it's at 1, and then this one does nothing. And this one starts to take my laser back down. And this is the moment of the pi pulse. And then it will go down, and it will go up, and it will go down, and it will go up. It's, by the way, not different from a regular oscillator, or if you want, a pendulum or a swing. Okay, so when we swing, let's say when we swing ourselves, not when someone swings us, and we do this thing with the legs, okay, and we keep swinging indefinitely, what we do is what the laser does. We drive at the right frequency so that we keep on swinging.
What happens if you don't put your hand in there?
So I mean that will continue indefinitely. Like at some point it will go down. There's so many interesting stuff to say about this. Like for example, when it's here in the center, how does it know if it needs to go up or down? It's 50-50. You know the answer?
It's just continuing because you have
No, not inertia. No, the reason it's not inertia. If I stop here, it's 50-50. I can stop and wait an hour, and then I come back. I lift my hand. It will continue upwards. It knows where to go. Something keeps the information about the direction. And this something, by the way, is the sign. If it's 0 plus 1, it means we're here, or 0 minus 1, which means we're here. But the sign of the superposition tells it where to go next.
No, I'm just thinking if the error correction, the efforts to do error correction needs now to take into account inherent error correction that comes within the deviation in the laser itself, in the frequency intensity, because you added variable to the equation that come from a third party. So now
Yeah, so
you
I
have
mean,
other.
I agree. If you think about this as part of the process, epsilon, then that's okay. That will be taken care of by the error correction. But if this is part of the error correction process, yeah, then you need to correct the error correction.
Yeah, you need to correct the error.
Bootstrap.
Oh, right.
At least that we know how to do pretty well. And if you kind of wondered how we do a Z-gate, that's even simpler. The only thing you need to do, you need to jump the phase of the laser by 180 degrees. You don't even need to do anything to the qubit, to the atom. Because the whole reference frame here is now the laser. The laser is an oscillator, it's like a stopwatch, and you simply jump the stopwatch by half of the period. There is a better way to see this, so don't worry if you don't see it already. But kind of to summarize this, just by playing with the frequency, intensity, phase, duration, shape of my laser, I can actually scan the frequency. I can do all sorts of tricks. I can implement any arbitrary 1 qubit.
So I have a question. So you chose an atom that has two levels of electrons, right? If you keep going, you don't put your hand in there, why doesn't it go to the second level?
Yeah, you're right. Let's see. All right. So for example, if this is the case, many mistakes, this transition will be very efficient because I'm going to use lasers that are approximately that frequency. But to go from here to here, I actually need a very different frequency. In this particular kind of example, there is a red photon and the purple photon, like really purple in the lab. And the red photon would just be very inefficient. So there would be some coupling. As we already said, coupling is also allowed when the frequency does not match, but it becomes much less and less efficient. So you have to break the uniformity of the ladder in order for a multi-level system to become a qubit. This is what superconductor transmon qubit do. This is the whole essence of superconducting circuits, is that they found a way to break the linearity. Because regular circuits, capacitors, resistors, inductors, they are all linear. They do not break. So they put in something very non-linear to break this, and then that allows it to be halt. Like to.
Would you say that F is defined as omega?
And just the regular notation where you see everywhere is uses omega here. Omega is called the Rabi frequency.
Okay.
Capital omega. And this is another reason why not to do this, because then this one is omega and this one is omega, and then I need to tell you capital omega and lowercase omega. I just decided to go for it. Rabbi is this guy, Isidore Isaac Rabbi. He actually got a Nobel Prize. He got this for the advancements in NMR, before there was MRI, actually. His first scientific paper, written on the design of the Rayleigh condenser, was published in Modern Electronics when he was in elementary school. This guy knew what he was doing. After reading about Copernican heliocentrism, he became an atheist. It's all very simple, he told his parents, adding, who needs God? As a compromise with his parents, for his bar mitzvah, he gave a speech in Yiddish about how electric light works. So this is Rabbi. These are Rabbi oscillations. This is a pi Rabbi pulse. This is a pi half Rabbi pulse. Omega, which is F, is the Rabbi frequency. It's very important. This guy was very important in so many things. You may recognize this guy that played him in Oppenheimer. So if you saw Oppenheimer, this is like a very important role. So this is Rabbi. All right, back to math. I know you're happy now. It's kind of very cool that everything we do to the atom using lasers could be shown on the Bloch sphere. Right? For example, kind of the way you do that is we are going to rotate the Bloch sphere around some direction, a torque vector in yellow. And the direction is determined solely by the laser. Take the intensity of the laser and the phase of the laser. That gives you the direction of the vector in the XY plane. And the frequency of the laser is the coordinate in the Z plane. So you can rotate the Bloch sphere in many ways, like for example, this rotation. If delta is 0, phi is 0, this is radio oscillation regular. We only have this guy. See? This means that the torque is pointing to the x direction, minus x. And this rotates the whole field that called Skrilagat, and you get an x gate. And you can do any arbitrary rotation using just laser fields operating on atoms. So super powerful. Now, what exactly qubit do we usually use? So single qubit gates, usually when we use real atoms, we do this to the spin of the atom, not to the orbit of the electron. The spin of the electron is more stable. So we actually look usually on this type of atoms. This is an atom. I mean, the atom have many states, but we look at three particular levels. We have a level where the spins point down. We have a level where the spin point up. We call this 0 and 1. And then there is another level. And lasers, when I shine lasers on this atom, it only couples one of these to the top. Okay? This is a very small frequency, and this is very large frequency. And here I also plot the shape of the electron. This is fifth orbital electron. And it turns out that if you shine light like that, it could emit like that, which means that the spin will flip. Or you can shine like this, and it will emit here, and the spin will flip like that. Or you can shine both of them, and deliberately take the spin and flip it, and flip it back, and flip it back. So everything I told you about Rabi oscillations between two electronic states can be done also to any arbitrary two states in a three-state system. And the guy who discovered that is called Raman, Chandrasekhar Vivanakata Raman, or Raman, and he got a Nobel Prize. He was the first non-white to get a Nobel Prize, and he got it particularly for this. And we now know how to do that, Raman transition, using lasers to flip a spin in a single site with 99.9% fidelity. And we can do an X gate, which is rotating. No, that's the opposite. This is the X gate, this is the Z gate, or any of these Y gates. All right? What about 2 qubit gates? Okay, 1 qubit gate is easy because you're operating with your laser on an atom. 2 qubit gates are no longer simply operating stuff on an atom, because we need to make atoms interact with each other. That's where the actual physics of the atoms get into this. And this is not trivial. And probably this was the thing that allowed eventually those the atomic neutral atom computers to evolve. And this was, say, demonstrated for the first time around 2016 or so. Well, maybe 2009. First demonstration, but really a gate only around 2016, 2018. The idea, remember my 3 states? Down, up, and the one that we coupled with the laser to? We're now going to add the 4th state, another laser, that's a different transition, so this requires a different laser. By the way, blue. And this excites the electron. Previously, we were walking kind of close to the nucleus. This excites the electron to a very far orbit. Okay? Atoms usually have a size of about an angstrom, 10 to the minus 10 a meter. These atoms are 1,000 times larger, or even 10,000 times larger. These are called Rydberg electrons, or Rydberg orbitals. It's taking the electron from an angstrom and putting it 10,000 times further away from mommy, and it kind of rotates. Right? Very, very far. So far that there might be atoms around. Like this,
it stays in orbit.
It stays in orbit, so this boy that rotates around mommy is like meeting many other people on the way, but it doesn't care. Eventually it will come back.
How come there's enough power?
You're assuming that all of the other people, all the other atoms are neutral. Mommy is the only one that is charged. All right? And enough with this analogy. And
So it's the power of magnetic
it's a
power.
Coulomb, it's electric power. The nucleus that is left behind is an ion, it's called an ionic core, and it's charged, and it pulls the electron back. But as long as it stays in orbit, it acts as a very strong antenna. So this would be one atom that we excite the electron here, like to be an antenna. That's another atom that is also now an antenna. And then the interaction between them, which is simply now an antenna-antenna interaction that we call dipole-dipole interaction, is enough to introduce phase and make a gate. To give you a feeling for the gateness in here, imagine that all of this transition, yellow plus red, it only works on the upspin. If the electron is in the downspin, it stays down. So you see, only if both atoms are in the upspin, only then both of them will become antennas and they will talk. Right? Like both of them have, I don't know, cellular
That creates interference?
No, it's I think about this as a phase accumulation. So there is an interaction and it changes the phase. So if both of them are in zero, nothing happens, 0, 0. So if it's a superposition with 1, 0, nothing happens. 0, 1, nothing happens. But then if there is a 1, 1 component, if the atoms are at 1, 1, they start to accumulate phase. And then I could change the sign from plus to minus, which is an entangling gate. So already in this picture you see an entangling gate. The interaction only happens if both atoms are at 1. There are kind of more sketches for this. You see two atoms with the core and the Hilbert electron, the electron that went up, and another one with some distance. And this you may recognize from your high school studies of physics. This is it looks like the hydrogen atom. Anyone recognizes the hydrogen atom? No? Okay, we have one. So you see many, many states of the electron, but then very, very close to the edge, there are those really, really cool Hilbert states.
What's the typical physical distance between these atoms to interact?
5 microns.
5 microns.
That's a lot. That's pretty big for optics. Optics has a resolution of a micron, so you can kind of relatively easily hold an atom in place, another atom 5 microns away, and then ask them to interact. And if you don't want them to interact, you separate them to 20. They're completely not interact. The scaling of this interaction with distance is so strong that 5 is full interaction and 20 is zero interaction.
The reason the video is for the excitation. energy.
Rubidium is convenient because the excitation energy is convenient. It's in the near IR lasers. It's heavy enough so that it's easy to hold. It has all sorts of strong optical transitions. It has a bunch of good properties, but it's not the only one. I mean, the cesium is probably
You can do it with sodium.
sodium, potassium, rubidium, cesium, maybe also lithium, but harder. That's the first column of the periodic table, and then in the second column, more options. Erbium, strontium, erbium.
Kind of metal.
All of them are metal. Yeah, it's metallic. Ask the students tomorrow to show you the metal rubidium. But it looks like any other metal. All right. For the sake of time, let me skip the. I'll just show you the animation of like how a gate would work. And you imagine something that looks like that, and then it only goes up. It works. If it doesn't go up. So eventually you get a gate. And this gate have a potential to have 4 nines, 10 to the minus 4. But currently they are at 99.8. 99.8 was published a month ago. And one of the authors is Ran Finkelstein, who's a professor in Tel Aviv, who was my student. So he holds the world record for a 2-qubit gate of 2 atoms. Okay, so that's for gates. And then if you remember De Vincenzo, we also need to prepare and to detect. Okay? Preparing and detecting also done with lasers, not surprising. I remind you, if you put an atom in the excited state, at some point it will decay by itself. You don't really need the laser to take it down. If you wait enough, it will emit photons. Usually when we use lasers to do this up and down, the photons that are emitted, so to speak, they live with the laser. So you don't see any photons coming out. But sometimes the photon will simply be emitted spontaneously to all around, and we can use this in order to prepare and to detect. So for example, preparing would look like that. That's one example. Your spins are either up or down, right? So you would use a pi pulse in order to take them from up to excited, and then you wait. At some point they will emit, they will decay. They will either decay to up or to down. Then you put another pi pulse. Again you excite. But you excite only those that are in up, those that are in down you don't. Again, either up or down. After many, many cycles like that, the atom will end up in down, and this is how we would prepare the atom in the down state. Or you can put a very good lens, good microscope objective lens, in front close to the atom, and collect the photons that are emitted, as many as you can, usually collect 2% of these photons, and look, like wait for them, actually measure them. And this will allow you to detect the state, to know if the atom is in up or down. That would be a measurement. You would shine a strong laser in here, and you will ask the atom to emit a lot of photons. And if it's in up, it will emit. And if it's in down, it will not do anything. It will be dark. So dark atom will be in 0, and bright atom will be in 1. And that will be your measurement. It will look something like that. You let the atom oscillate, and once in a while, tuck, it goes back to 0. You oscillate, tuck, 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 and you collect those photons. So everything is done with lasers, and this like summarizes it. Neutral atom quantum computer looks something like that. You hold the atom, you cool them down. We didn't talk about cooling yet. You put them in place. If you want a 1 qubit gate, you simply shine laser on them. If you want a 2 qubit gate, you take the atoms that you want two of them to interact, you put them together, you do this, take them back. You can read out. And there are many, many advantages to atoms. But I listed here just maybe a few. When atoms are all identical, that's good. You like your qubits to be identical. You don't want them to have different properties. You can collect many, many of them. In principle, they have a low coherence time, even 10 seconds at room temperature. The atoms themselves are at 0 temperature, but the whole apparatus is at room temperature. You can control them solely by lasers. You can change their position, so you can make them interact as you wish. Any atom with any atom, any qubit with any qubit. So it's all-to-all connectivity. So many advantages. Okay. Let me skip that, I'll skip that. Here is another picture from the lab. You will see this tomorrow. That's exactly the lab you're going to visit. If you have good eyes, you will be able to see the glass cell in the center and the objective lens that look inside. We'll show you how we cool down the atoms using lasers. It's going to be tomorrow. Here are more pictures from other sides. This illustrates how the lens generates the focus in different foci and all the atoms. And by the way, it's very cool because we can use all sorts of electro-optic tools. For example, to change the direction of the laser beam that enters the lens. And if you know a bit of optics, you know that the direction of a laser beam that enters the lens changes the focus where this laser beam will be focused. And so this is how you move atoms, just by changing the angle of the laser beam that enters the objective. And I'll wrap this part up by showing you a small movie. It's taken from Harvard and Quera. It's a company in Boston.
Yuval will be on Wednesday. Yuval will be.
Fantastic. So maybe Yuval will also show you this one of how they take their atoms. So you see that they move them in plaquettes because I mean, you think about error correction. You take many, and you want those many to make gates with one. I mean, each plaquette of 16, say, represents one logical qubit, and then gates between those logical qubits between putting them together and shining all sorts of.
This is not an illustration. These are real atoms.
Real atoms died in this. Yeah, but there is some illustration part to this. In order to take this picture, they had to stop in every frame and image all the atoms, which means they killed the quantum information. So in order to make the movie, they just, they halted the computation in many, many different points and just took a picture of everything. And this is like an average picture of all of those frames. For a moment there, you could see that they are using some code of error correction, which is using these 8 qubits. I remind you, 5 is enough. We could do this with 8. And the way we do this with 8 is by putting them on a bit like a cube. So we talked about surface codes that are 2D codes, but this is like a demonstration of a 3D structure of an error correction code. Okay, and now in the last 15 minutes we have, let's talk a bit about, well, I'm sure you will hear a lot about photons tomorrow and quantum source.
Also, before you move on, has anyone tried to use the spin of the nuclei instead of the spin of the
Yes,
orbits?
yes. In many different forms and shapes. In particular, there was a company, a very good one, but it's called Atom Computing. The first 2-3 years, they were kind of doing R&D on working with a nuclear qubit instead of a electronic qubit or an electric qubit. Electron spin, nuclear spin instead of electron spin. And that worked really, really well in terms of T1, T2 times, but it was very, very hard to manipulate otherwise and make 2 qubit gates. And they left it and went back to electron space. But in my lab, I think this lab you won't see tomorrow unless you really ask. We have a different experiment where we're trying to entangle 2 nuclear spins. I hope that this will be kind of interesting. All right, so now we want to encode qubits not on atoms but rather on photons. And this is really cool. Photons are really nice. And you can encode, similarly to atoms, you can encode qubits on them in many, many different ways. So remember, we only need to identify 2 states. So for example, one option is to have a single photon that is either in the top channel or the bottom channel. Top channel is 0, bottom channel is 1. This is the qubit. Okay, 1 photon. By the way, if I have no photons, it's neither here nor here, it's not in the qubit subspace. And you know, if I find it, if I recognize this, I could understand that then there was an error. Okay, that's cool. Because another option that I didn't write here is that I encode my qubit on either having a photon or not having at all, like 0 and 1. This is also 2 distinguishable states. The problem is that a loss of photon looks like the 0 logical. Whereas in here, a loss of photon is outside of the logical subspace, so allows me to recognize loss. Photons are easily lost, so that's good that we have a way to see that. That's one option. It's called the dual realm representation. Very, very important. That's what psi-quantum does and quantum source sort of. You could also encode the bit on frequency or color, so it'd be like a red and blue. And the advantage of that is that there are so many frequencies and so many colors, and you can generate in principle like 100,000, an entangled state of 100,000 different states. But it's also not very easy to even make like a 1 qubit gate. Like how do you make a superposition of blue and red and then make another? That's actually a very, very common and known basis is the polarization basis, which we discussed a couple of times. So that would be the electric field either doing that. That's 1 photon, electric field is doing that. That would be 1. And this is the same photon, but the electric field does this. So this would be 0. Okay. By the way, it's not exactly the same photon, but it's the same photon. Okay. So it's the same photon in a different mode. So it could be, then it would be horizontal and vertical and horizontal, which are these 2 states. But combinations of those 45 degrees would be other states on the Gauss field. So that's very, very convenient. You could also encode the photon on time. If the photon arrives early, it's 1. If it arrives late, it's 0. It's possible and also used. Or we talked about this 2 weeks ago. The photon could be like it's a laser beam. Could either have these 2 lobes or these 2 lobes, and that would be 0. And you can everything is allowed, and people have done everything. Let's look a bit more about the dual rail. Imagine that here I want to represent, so not psi1 but psi2, but rather a single qubit with the photon being either here or here. Okay. So if it's here, it's 1, and if it's here, it's 0. And this would be a B-splitter, which is simply a glass that transmits 50% of the time and reflects 50% of the time. And that means that if I have a photon in here, when it comes in here, it will become a superposition of either here or here. So this generates superposition. Well, it's not yet an interferometer. It's simply just one interferometer would require 2 mirrors. Split and rejoin. I don't rejoin, I only split. What type of gate is that? If this is a single qubit, this is right, Adama, that's right. Okay, so In a dual ray representation, it's extremely easy to generate superpositions. You simply need a half-reflecting mirror. If this is, by the way, an integrated circuit, then you simply need to make the waveguides close enough so that photons leak to the other channel. If you put a glass, just a thick glass in front of one of these, you make a phase gate. Change the phase of, if this was 1 plus 0, and now you put a piece of glass in here, it will become 1 minus 0. So super easy to manipulate single qubit gates in a dual ray representation. What about polarizations? It's also easy. This is supposed to be, this is important. So it's supposed to be an animation. It moves a bit, very slowly.
Slow for
Funny. So there is a polarization that oscillates vertically, and then inside this special crystal, it rotates by 90 degrees. It rotates like that. This is called a wave plate, and it performs rotation from horizontal to vertical, which means a Z gate, or an X, depending on where you look. It shows X here. Or you can put polarizers and everything. So rotation of polarization is something that we know how to do with optical stuff. So people mostly use these, dual ray representation and polarization, and often together in the same platform, because it's easy to go from one to the other. There is a cube, it looks like a cube, you'll see this tomorrow, that is called a polarizing beam splitter, and it's the one that translates from polarization qubits to dual ray qubits and back. So photons could encode qubits and very easily, and 1 qubit gates are easy. Generating photons is relatively easy. Here is the way we do this in the lab. We take our rubidium atom, we excite it to this doubly excited state, so that the electron, when it emits a photon, it emits 2 photons. It goes here, emits 1, right? And then emits another one, which I call out yellow. And if it emits 2 photons, we discussed this at some point, and you detect one, you know that the other one is also there. And this is a single photon source.
Unless you have a
Unless it's absorbed. For example, that might be like some dirt in here that would block the other one. All of these block, for example, in this particular territory, anything that, despite measuring a heraldic photon, somehow destroys your probability for your single photon is called heralding efficiency. Our heralding efficiency is only 10%. This is an experiment you will see tomorrow. This is why I put it, because what you will see tomorrow is an experiment where we generate single photons, and then we use a quantum memory to delay these photons until they are synced with another photon that is generated. Then we have 2, and then we make a gate. So you don't see the gating here, but it's in the lab. So there will be the whole series you will see tomorrow, right? But if you don't have a lab, you can purchase a single photon source from Tor Labs for $24,151.05.
Wow. 5 cents.
Well, this is the price.
It's the hour for us.
Yeah, the 5 cent. And this particular single photon source is a photon pair, correlated photon pair source, which exactly means that you would measure, there are 2 fibers that come out. If you measure a photon in one of them, the other one has a photon in it. So you can buy this commercially. And if you go to the Tor Labs site, you would actually be able to see the spec. You know, what is the heralding efficiency of my source? Like, what's the chances that indeed I have a photon and all of that? So that's very cool. It's not based on atoms per se, it's based on crystals, but that's technical. And lastly, going through the Vincenzo criteria, we want to detect photons, and this is a solved problem now. It wasn't that 20 years ago. We now have detectors that are called SNSPDs, superconducting nanowire single photon detectors. So they are based on, this is the detector, it's a zoom in on a very small piece of circuit. It's a wire, it's very, very thin, and it's cooled down, so you need a cryostat for that. And it's cooled down until it is superconducting. So when you run current through it, it runs a lot of current, and it's happy. Until 1 photon hits it. And it is so thin that the energy of 1 photon is enough to heat it up, to lift its temperature, and it becomes not superconducting. And then the current just stops. And you monitor the current, and when you see the current stopping, you know that there was a single photon with 98% detection efficiency. That's amazing. So we have this in the lab, and Quantum Source has it, and PsiQuantum presumably also integrates it into its circuits. So pretty cool. So photons are fantastic. They can encode qubits in different quantum. They could easily guide them on, kilometers or under the ocean. Okay, principle. They fly the speed of light, which is, it's a bug, but also a feature. They're easy to manipulate. They're relatively easy to generate. They're easy to measure. One problem is left. What is that?
Easily lost.
No, lost. Well, yes,
Control?
that's a problem.
Stabilizing.
Lost is a problem. Hmm?
Stability.
No, the time and loss is similar, but I'm talking about like a fundamental. Okay, interact. They do not interact. Okay. Photons. I don't know if you know. If you take two laser beams, you shine laser beams, and then you cross the laser beam, nothing happens. Right? This does not happen in real life. Photons do not interact. Okay, and that actually make photons very different from all other modalities. And when you always hear about photonic quantum computation, it always somehow not the same as what you've heard up until now. There is no circuitry, and the gates don't work similarly. So all of what we know up to now was a computation, was a sequence of operations and timing gates. For photons, it required a very different state of mind. For photons, that's kind of very generally, what people have found that you need to do is you need first to somehow generate a state, each point here is a photon, where the photons are all entangled to one another in a grid. Each of these photons is entangled to the 4 adjacent photons to it. Okay? This is called a cluster state. And only then, when it's ready, you are going to perform the calculation. The calculation then does not require any 2-qubit gate. So whatever is always come in a 2-qubit gate, the entangling gate, the interactions, this does not happen in photonic quantum computation, or at least not in the regular one. You first generate this somehow in a different approach, and then you come here, and the only thing you do measurements, or 1-qubit gates and measurements. So there is this grid, and instead of time, there is information flow. When you perform measurement, always when you measure, you feedback on the system, and when you're done measuring, the circuit is done and your calculation was performed. And it was proven that this approach, which is called one-way quantum computation, because every qubit is used once, or measurement-based quantum computation, because we always measure, is as strong as full kind of circuit-based quantum computation. So this generates a universal quantum computer. And this is due to these two people, Hausendorff and Briegel. May 2001, they wrote this one-way quantum computer, and this is like a 8 years later, they wrote this summary of what has evolved, and they changed it to measurement-based quantum computation. This is why it has 2 names. And then I'll read for you the abstract. We present a scheme of quantum computation that consists entirely of 1-qubit measurements, only measurements. But when you say 1-qubit measurement, it also involves rotations because you need to measure at different places. On a particular class of entangled states, a cluster state. So this is a cluster state. A cluster state is many qubits that are entangled pairwise. The measurements are used to imprint a quantum logic circuit. You imprint a quantum logic circuit on the state, thereby destroying its entanglement at the same time. So when you measure, keep on destroying entanglement. Cluster states are thus one-way quantum computers, and the measurement form the program. The algorithm that you want to run in that particular run is implemented by the series of measurements that you do and the feedback that these measurements make on the other measurements that you make. And there is really like nice rules that we do not go over. Like what does a Z measurement do? what does the X measurement do? And so when you measure in X or Z, it performs different type of manipulation to this graph, and you measure, and when you finally get to the end, you make a universal quantum computation. And a homework task, if you want, try to construct this 1D cluster state. And this is how you do it. You perform a Hadamard on all gates, and then you perform a conditional phase on all pairs of qubits. That's it, and this order doesn't matter. So try this and see how you generate this, or if you really want to try to like make a 3x2 cluster state. To wrap up, I mentioned that okay, so this is kind of cool, but the challenge now is transformed in photonic quantum computation to make these clusters. So measurements is easy. 1 qubit gets easy. The challenge is to make the cluster state, and this is what psi-quantum is all about, and quantum source is also all about. How to make a state with many single photons that are all entangled to each other. The problem again is that photons do not interact, and the only thing that photons do is this process. They do something which is called probabilistic entanglement, which is due to, again, Laflamme and Milburn and Mill, which is this process. This is a process that is really, really special and unique in quantum. If you send 2 photons to a beam splitter, then they will either both go up or both will go down. They will not, you will not see the options of the split. This is called Hongu-Mandel interference. It was known for many years.
One is splitting.
Hmm?
One is splitting.
No.
If
Both
you
of
would
them, they decide together if to go here or here.
Yeah, but if you would talk only one, then it would split.
Yeah, either one reflects or the other one reflects, but not both of them reflect and not both of them transmit. In fact, all 4 options do happen, but they're both transmitting and both reflecting destructively interfere, and they disappear. This is due to really quantum destructive interference. It's a really quantum effect that has no classical analogy. And notice that this looks like an entangled state, more or less. Either 2 are here or 2 are here in a superposition sense. And so this is kind of entangled. It's just that you end up with either here or here, and so this is called probabilistic entanglement. And if you want, you can go over this at some point later on and see that if you do that, you use auxiliary photons, you measure on some particular cases of measurement, the 2 photons that come here become entangled. It's called the fusion gate, and this is what fusion-based quantum computation is based on. And this is the kind of workhorse of psi-quantum and quantum source, generating entanglement that grows and grows until you get a cluster state. By the way, it's not easy, and it requires a lot of resources. So for example, psi-quantum, imagine that they would have this factory where there would be many billions of those fusion gates inside, all of them probabilistic. So it's hard to grow, but if you make enough resources from the beginning, you are able to grow the cluster state until the cluster state is large enough, and you can perform some useful quantum computation. But look at this sheer size of this thing. Compare this, for example, to these neighborhoods. Okay. All right.
So what do you get out of it? You get a single beam.
So yeah, what comes out? No. So you have. Let's suppose that, just to simplify, let's suppose that each photon is in a different waveguide on the chip. So you have 10,000 waveguides, and they are entangled in a cluster state connectivity. And that now you measure, and you know you're done. But to entangle them is the scaling challenge, because each and every timing operation is probabilistic, and you need like some exponential resource to start with, exponential resource until at the end you get a good cluster state. All right, so that's it.